In the beginning, there was nothing. No space, no time, no matter, no energy. Then, 13.8 billion years ago, everything exploded into existence in an event so violent, so incomprehensible, that it forged every atom in your body, every star in the sky, and the very fabric of reality itself. This is the story of the Big Bang, the beginning of everything. The universe began as a singularity, a point infinitely small and impossibly dense, containing all the matter and energy that would ever exist. In a fraction of a second, this point erupted outward in the most energetic event in history. Space itself expanded faster than the speed of light, creating distance where none existed before. Time began to flow forward. The laws of physics crystallized into being. In the first trillionth of a second, the fundamental forces that govern our reality, gravity, electromagnetism, and the strong and weak nuclear forces, separated from a single, unified superforce. The universe was born. But how can we be so sure this happened? The evidence is overwhelming, written across the cosmos itself. Every galaxy we observe is rushing away from us, a clear sign that the universe is expanding. If you rewind this cosmic movie, everything converges back to a single point, approximately 13.8 billion years ago. We can still see the afterglow of the creation event, the cosmic microwave background radiation. It's an echo from when the universe was just 380,000 years old, visible in every direction we look. We can even measure the precise amounts of hydrogen and helium cooked up in the universe as first few minutes. The story of our origin is all around us. So what came before the beginning? This question might not even make sense because time itself began with the Big Bang. Asking what came before is like asking what's north of the North Pole. Still, physicists can't help but speculate. Perhaps our universe bubbled up from a quantum fluctuation in a vast multiverse. Maybe it's the result of a bounce from a previous collapsed universe. Some theories suggest it formed from a black hole in a higher dimensional space. Or perhaps the most mind-bending idea of all, the universe simply willed itself into existence from quantum uncertainty, a realm where the laws of physics allow something to emerge from absolute nothing. The universe's 13.8 billion year history is a truly remarkable timeline. In the first trillionth of a second, the fundamental forces separated, and space underwent an exponential growth spurt called inflation. Within the first second, quarks, the building blocks of matter, combined to form protons and neutrons. After just 3 minutes, the first atomic nuclei were forged. For the next 380,000 years, the universe was a hot, dense fog. Then it cooled enough for atoms to form, allowing light to travel freely for the first time, creating that cosmic microwave background we still see today. 200 million years after the Big Bang, the very first stars ignited, lighting up the cosmic darkness. Over billions of years, galaxies formed and merged. Then 9 billion years after the Big Bang, our own solar system condensed from a swirling cloud of gas and dust. And finally, 13.8 billion years later, here we are. The universe has become conscious, able to look back and piece together the story of its own origin. It's a common misconception that the universe is expanding into some empty void. That's not quite right. Space itself is expanding, carrying galaxies along for the ride, kind of like raisins in a rising loaf of bread. The farther away a galaxy is, the faster it appears to move away from us. In fact, the most distant galaxies we can see are receding at speeds faster than light. This isn't breaking Einstein's laws because it's not the galaxies moving through space. It's the fabric of space, between us and them, that's stretching. This incredible discovery, made by Edwin Hubble in 1929, provided the first solid evidence for the Big Bang and completely revolutionized our understanding of the cosmos. In its first moments, the universe was unimaginably hot, trillions upon trillions of degrees, far hotter than the core of any star. At these insane temperatures, matter as we know it couldn't exist. It was just a scorching hot soup of fundamental particles and pure energy. As space expanded, it cooled down, much like the air escaping from a compressed can. This cooling was the key. It allowed particles to start combining into more complex structures. Within microseconds, quarks clumped together to form protons and neutrons. After 3 minutes, these fused into the first atomic nuclei. It took another 380,000 years for the universe to cool enough for electrons to join these nuclei, finally creating stable atoms. The universe transformed from a featureless, opaque plasma into a transparent cosmos where light could travel and the seeds of structure could be sown. And this brings us to you. We are all intimately connected to the Big Bang. The hydrogen in the water that makes up over half your body was forged in the first 3 minutes of cosmic history. The heavier elements, the carbon in your cells, the nitrogen in your DNA, the oxygen you breathe, were all created in the hearts of stars that lived and died long before our sun ever formed. We are literally made from the ashes of the Big Bang and the stardust of long-dead stars. In a very real sense, we are the universe's way of knowing itself. What if I told you that in less time than it takes to snap your fingers, the entire universe went from a state of unimaginable mystery to a recognizable cosmos? The story of everything begins not with a bang, but with a series of mind-bending transformations, all within the very first second. The universe's first moment, a period lasting just 10 to the minus 43 seconds, is called the Planck epoch. It's an era so extreme that our understanding of physics completely breaks down. Space-time itself wasn't smooth, but a roiling, chaotic quantum foam. To truly understand this instant, we need a theory of quantum gravity, one of the holy grails of modern physics. For now, the universe's absolute beginning remains its deepest secret. Then, from that unknowable instant up to 10 to the minus 36 seconds, came the grand unification epoch. The temperature was over 10,000 trillion degrees. It was so hot that 3 of nature's fundamental forces, the strong, weak, and electromagnetic forces, were merged into a single unified superforce. As the universe expanded and cooled, this perfect symmetry shattered, and the strong nuclear force broke away, becoming its own distinct entity. This led to the most dramatic event in cosmic history, cosmic inflation. Between 10 to the minus 36 and 10 to the minus 32 seconds, the universe expanded exponentially. It doubled in size, then doubled again and again at an astonishing rate. In a fraction of a second, the universe ballooned from smaller than an atom to about the size of a grapefruit. This incredible growth spurt smoothed out the fabric of space-time and planted the seeds for all future structures, the galaxies, stars, and planets we see today. What powered this incredible expansion? A hypothetical energy field called the inflaton. It filled all of space with a tremendous energy density, creating a kind of negative pressure that forced space to expand. When inflation ended, this field decayed, releasing all its stored energy in a process called reheating. This massive energy dump filled the young universe with a hot, dense soup of particles and radiation, the event we often think of as the Big Bang itself. From 10 to the minus 32 to 10 to the minus 12 seconds, we entered the electro-weak epoch. As the universe continued to cool, another crucial symmetry broke. The electromagnetic and weak forces split apart. This separation was driven by the famous Higgs field, switching on across the cosmos. Before this, fundamental particles were massless, but as they began interacting with the Higgs field, they acquired the mass that we know today. This is the moment matter truly became matter. Next up, the quark epoch, lasting until 1 microsecond after the Big Bang. The universe was a seething soup of fundamental particles called quarks and gluons, known as a quark-gluon plasma. The temperature was still too high for quarks to bind together. They roamed freely in a state of matter so extreme we can only recreate it for fleeting moments inside powerful particle accelerators like the Large Hadron Collider. At the 1 microsecond mark, things cooled enough for the Hadron epoch to begin. The strong force finally became powerful enough to confine quarks, binding them together in groups of 3 to form protons and neutrons, the building blocks of every atomic nucleus. This process, called confinement, is so strong that to this day, no free quarks have ever been observed in nature. The universe had just created the raw materials for atoms. From 1 second to 10 seconds, the lepton epoch took over. The universe was dominated by lighter particles like electrons and their antimatter counterparts, positrons, which were constantly being created and then annihilating each other. Meanwhile, ghostly particles called neutrinos stopped interacting with everything else and began streaming freely through space. They're still out there today, an invisible cosmic echo of the first second. But this brings us to one of cosmology's greatest puzzles. In the beginning, matter and antimatter should have been created in perfectly equal amounts. If so, they would have annihilated each other completely, leaving behind nothing but light. So why is there anything here at all? The answer seems to be a tiny, unexplained imbalance. For every billion pairs of matter and antimatter particles, there was just one extra particle of matter. After all the annihilation was over, that tiny remnant was left over, and it became everything we see and are. After about 10 seconds, the mass annihilation of electrons and positrons was complete, leaving photons, particles of light, as the dominant form of energy in the cosmos. For the next tens of thousands of years, the universe was an opaque, glowing fog. Light couldn't travel far without scattering off a free electron. The cosmos was brilliantly bright, but you couldn't see a thing through the glare. So, in just 1 second, the universe transformed. It went from a point of infinite density to a hot plasma of protons, neutrons, and electrons. The fundamental forces separated, space inflated, particles gained mass, and matter narrowly won its battle against antimatter. This single, incredible second set the stage for the next 13.8 billion years of cosmic evolution. How can we possibly know any of this? We test these ideas by smashing particles together at incredible energies in accelerators, recreating the conditions of the early universe. We see the leftover heat from the Big Bang imprinted on the cosmic microwave background, which carries evidence of inflation, and the amounts of simple elements in the universe match our predictions perfectly. It's a stunning convergence of theory and observation. Of course, huge questions remain. We don't know what came before inflation, or what the inflaton field really was. The origin of the matter-antimatter asymmetry is still a puzzle, and the nature of dark matter and dark energy, which make up 95% of our universe, is completely unknown. 3 minutes after the Big Bang, the universe had cooled to about 1 billion Kelvin. Now that's still mind-bogglingly hot, but it was just cool enough for nuclear fusion to kick off. This incredibly brief window, lasting only about 17 minutes, was a pivotal moment. It was the cosmic event that would lock in the chemical recipe of our entire universe for billions of years to come. Between 3 and 20 minutes after the Big Bang, the universe transformed into a colossal nuclear reactor. Protons and neutrons, which had popped into existence in the very first second, could now fuse together, overcoming their natural repulsion. The process started with something called deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. Before this point, any deuterium that formed was instantly blasted apart by high-energy photons. But as the universe cooled, deuterium could finally survive. This opened the floodgates. Deuterium nuclei started fusing with protons, creating helium-3. Then helium-3 combined with neutrons to forge helium-4, the stable, familiar helium we have today. By the time this cosmic cooking show ended at the 20-minute mark, the results were in. About 75% of the universe's ordinary matter remained as hydrogen, basically single protons. The other 25% had been fused into helium-4, along with tiny traces of deuterium, helium-3, and lithium. This 3-to-1 ratio of hydrogen to helium is incredibly precise and universal. No matter where we look, any cloud of primordial gas that hasn't been touched by stars shows this exact same ratio. It's one of the most powerful and successful predictions of the Big Bang theory. When we observe ancient gas clouds at the edge of the visible universe, they confirm these abundances perfectly, giving us rock-solid evidence that this all really happened. So why did this fusion frenzy stop with just the light elements? It all comes down to expansion and timing. As the universe expanded, it cooled. Within 20 minutes, the temperature dropped below 100 million Kelvin, too cold for fusion to continue overcoming the electromagnetic repulsion between nuclei. The window of opportunity slammed shut. Also, there's a crucial roadblock. There are no stable nuclei with 5 or 8 particles. To make something heavier like carbon, you need to fuse 3 helium nuclei at once, which was almost impossible in the diffuse, rapidly cooling early universe. That kind of high-stakes fusion would have to wait for the intense pressure cookers inside of stars, which wouldn't form for hundreds of millions of years. The Big Bang made the ingredients. Stars would later do the rest of the cooking. There's another fascinating wrinkle in this story: the neutron decay problem. Free neutrons, when left on their own, are unstable. They decay into a proton, an electron, and an antineutrino, with a half-life of about 10 minutes. In the very first second, neutrons and protons could freely transform into one another, keeping a perfect balance. But as the universe cooled, these reactions froze out, fixing the neutron-to-proton ratio at about 1:7. From that point on, neutrons could only decay, they couldn't be created. This put fusion on a strict time limit. The neutrons that managed to get locked into helium-4 nuclei were saved, stabilized by the strong nuclear force, but any that were left over were simply lost to decay, which slightly tweaked the final amount of helium we see today. Big Bang nucleosynthesis also cooked up a tiny amount of lithium-7, about 1 atom for every 10 billion hydrogen atoms. But here's where a mystery pops up, known as the cosmological lithium problem. Our calculations predict that there should be 3 to 4 times more lithium in the universe than what we actually observe in the oldest stars. This discrepancy has stumped scientists for decades. Is it because of some unknown nuclear reaction that destroys lithium? Or maybe processes inside stars that deplete it from their surfaces? Or could it even be a hint of new physics beyond our current understanding? The lithium problem is a great reminder that even our most successful theories still have intriguing puzzles left to solve. You might be wondering, why didn't the Big Bang make elements like beryllium and boron? It's because these elements have a stability issue. There just aren't any stable isotopes in the mass range that was accessible during that brief fusion window. For example, if you fuse 2 helium-4 nuclei, you get beryllium-8. But beryllium-8 is incredibly unstable. It decays almost instantly, splitting right back into the 2 helium nuclei it came from. This instability created a major bottleneck, preventing the chain of fusion from building up to heavier elements. Beryllium and boron were created much later, when cosmic rays smashed into heavier elements out in space, but the Big Bang itself just couldn't forge them. So how can we be so sure about all this? Well, we test the theory by looking back in time. Astronomers point their telescopes at the most ancient gas clouds in the universe, ones that have never been mixed with material from stars. When light from a distant quasar passes through one of these clouds, the gas absorbs certain frequencies, leaving a chemical fingerprint in the light spectrum. These observations consistently show the exact abundances the theory predicts: 75% hydrogen, 25% helium, and trace amounts of deuterium and lithium. The agreement between the predictions and what we actually see is nothing short of remarkable, making it one of the strongest pillars supporting the Big Bang theory. No other idea explains these precise primordial abundances so naturally. Amazingly, this process also helps us understand one of the biggest mysteries in cosmology: dark matter. The amount of helium and other light elements created in the Big Bang is extremely sensitive to the density of normal or baryonic matter. By measuring the observed abundances, we can calculate precisely how much baryonic matter exists in the universe, and it comes out to only about 5% of the universe's total mass and energy. This number perfectly matches independent measurements from the cosmic microwave background, and this leads to a stunning conclusion: dark matter cannot be made of normal matter. There's about 6 times more dark matter than baryonic matter, so it has to be something else entirely. Some kind of exotic, invisible particle that we have yet to discover. So, after just 20 minutes, the universe had its first chemical inventory: hydrogen, helium, and a few trace elements. For the next few 100 million years, this was it. The entire cosmos consisted of just these simple primordial elements. No carbon, no oxygen, no iron, none of the heavier elements essential for life as we know it. Those would have to wait, forged in the hearts of stars over cosmic timescales. But the foundation was laid. From these incredibly simple beginnings, all the complexity of the universe would eventually emerge. And those very elements created in the Big Bang became the raw material for the very first stars. These pristine giants, called population 3 stars, were formed from pure hydrogen and helium. Inside their fiery cores, they fused hydrogen into helium, just like the early universe did. But they didn't stop there. Their immense temperatures and pressures allowed them to forge carbon, oxygen, and even heavier elements. When these stars died in spectacular supernova explosions, they scattered these new elements across space, enriching the cosmic gas that would form the next generation of stars and planets. Every single element in your body heavier than lithium was made inside a star, but those stars themselves were born from the aftermath of Big Bang nucleosynthesis. Today, the study of Big Bang nucleosynthesis remains a cornerstone of modern cosmology. Precision measurements of these primordial abundances help us constrain fundamental properties of our universe, like its density, its early expansion rate, and even the number of different types of neutrinos. Any tiny deviation from the predicted abundances could be a signal of new physics waiting to be discovered. Astronomers continue to hunt for even more pristine gas clouds, using bigger and better telescopes to peer ever closer to the beginning of time. With nucleosynthesis complete, the universe entered a new phase. For the next 380,000 years, it was a hot, dense, opaque plasma of nuclei and electrons. But the elements were in place, the cosmic stage was set, the matter that would one day form galaxies, stars, planets, and us had been created. Now, it was simply a matter of waiting for the universe to cool enough for atoms to form, and for the grand tapestry of cosmic structure to begin weaving itself together. For about 380,000 years, it was a place you wouldn't recognize, a completely opaque, brilliant fog. If you could somehow go back in time, you wouldn't see stars or galaxies, just a blinding, featureless glare in every direction. This era is called the Cosmic Dark Ages, which is a bit ironic because the universe was actually filled with scorching hot light. The problem was, this light couldn't go anywhere. In this early period, the entire universe was a plasma, a superhot soup of electrically charged particles. Electrons, not yet bound to atoms, zipped around freely. Photons, the particles of light, couldn't travel more than a few inches before slamming into one of these free electrons and scattering in a random direction. It was like trying to see through the thickest fog imaginable. Matter and radiation were locked in a cosmic dance, so tightly coupled that they moved together as a single fluid. This constant scattering meant light couldn't escape, and the plasma couldn't cool down efficiently. The temperature was pretty much the same everywhere, but tiny seeds of future structure, planted during cosmic inflation, were already starting to grow. Around 47,000 years after the Big Bang, a huge shift happened. We call it matter-radiation equality. Before this, the universe's energy was mostly from radiation, those countless photons bouncing around. But as the universe expanded, something interesting occurred. The density of matter decreased as the universe got bigger, but the energy of radiation dropped even faster because its light waves were also being stretched out and weakened. Eventually, the influence of matter overtook the influence of radiation. This was a game changer. When radiation was in charge, its immense pressure smoothed out any clumps of matter that tried to form. But once matter took the driver's seat, gravity could finally get to work, pulling matter together and starting to build the cosmic web we see today. And here's where a mysterious ingredient comes into play: dark matter. It was the unsung hero of the Dark Ages. Unlike normal matter, dark matter doesn't care about light or radiation. It only feels gravity. So while normal matter was still trapped in that foggy plasma, dark matter was already free to start clumping together. It began forming vast, invisible structures like a cosmic scaffolding. These were the gravitational wells, the cosmic potholes, where normal matter would eventually gather. These dark matter halos grew throughout the Dark Ages, quietly setting the stage. When normal matter was finally set free, it fell right into these pre-existing structures, giving galaxy formation a massive head start. Without dark matter, our universe might look very, very different. Throughout this entire period, the universe was constantly expanding and cooling. Think about it. At around 10,000 years old, the universe was about 10,000 Kelvin, as hot as the surface of a star. By 100,000 years, it had cooled to around 3000 Kelvin. The density also plummeted. What started as something denser than an atomic nucleus had expanded into a gas more diffuse than the air you're breathing, though still much denser than deep space is today. This cooling was the inevitable result of expansion, spreading all that energy and matter out over a larger and larger volume. And this relentless cooling was leading the universe towards its next great transformation. But the early universe wasn't quiet. It was ringing like a giant cosmic bell. These were acoustic oscillations, basically giant sound waves sloshing through the plasma. Imagine a tug of war. Gravity would pull a clump of matter together, making it denser and hotter. But then, the intense pressure from radiation would push it back apart. This constant push and pull created massive pressure waves that rippled through the cosmos at nearly the speed of light. These oscillations happened on all scales, from small ripples to continent-sized waves. And when the universe finally cooled enough for atoms to form, these sound waves were frozen in place, leaving a permanent imprint on the light from that era, an echo we can still detect today. As the universe neared the 380,000-year mark, it was on the brink of a radical change. The temperature had dropped to a critical point, about 3000 Kelvin. At this temperature, the photons zipping around were no longer energetic enough to instantly knock an electron away from a proton. The conditions were finally right for stable, neutral atoms to form. For its entire existence, the universe had been an opaque, charged plasma, but it was about to become a transparent gas, allowing light to travel freely across the cosmos for the very first time. The stage was set for the universe to finally light up. This moment is called recombination. It's a slightly confusing name since this was the first time electrons and nuclei were combining, not recombining. As the temperature dropped below that 3000 Kelvin threshold, electrons started getting captured by protons, forming the first neutral hydrogen atoms. This wasn't like flipping a switch. It was a gradual process that took about 100,000 years. As more atoms formed, there were fewer free electrons to scatter light, which allowed the universe to cool even faster, accelerating the process. Eventually, almost all the charged plasma had turned into a neutral gas. The cosmic fog had finally lifted. The moment the universe became transparent, all the light that had been trapped inside was set free. These photons began streaming across the cosmos unimpeded, and they have been traveling ever since. This ancient light is what we now call the cosmic microwave background, or CMB. When it was released, it was visible light, corresponding to the 3000 Kelvin temperature of the universe at the time. Now, if you look at a map of the CMB, you'll notice it isn't perfectly smooth. The cosmic microwave background is an absolute goldmine of information. Its average temperature tells us how much the universe has expanded. The size of those hot and cold spots reveals that the geometry of our universe is almost perfectly flat. The specific patterns in the fluctuations are the frozen sound waves from the plasma era, telling us what the universe was made of. Even the way the light is polarized holds secrets about gravitational waves from the first moments of the Big Bang. From this single snapshot, this one ancient light, we've determined the universe's age, its composition, and its expansion rate with stunning precision. It is without a doubt the most important discovery in all of cosmology. After this great release of light, the true dark ages began. The universe was now transparent, but it was also dark. The CMB light had faded and redshifted out of the visible spectrum, and not a single star had yet been born. For the next 200 million years or so, the universe was filled with nothing but vast, dark clouds of hydrogen and helium gas, slowly, silently, collapsing under the pull of gravity. It was a simple universe, without light, without chemistry, just primordial gas, waiting for the right conditions to finally ignite. But even in the darkness, the universe was anything but still. Gravity was working tirelessly. The neutral gas flowed into the invisible dark matter halos that had formed earlier, making the densest regions even denser. Those tiny fluctuations we see in the CMB were being amplified, growing into the first large-scale structures. The universe's first proto-galaxies were beginning to assemble in the dark. Within a few 100 million years, some of these collapsing clouds of gas would become so dense and hot that they would trigger nuclear fusion at their cores. The cosmic dark ages were drawing to a close, and the first stars were about to light up the cosmos, ending the darkness once and for all. Between 200 and 400 million years after the Big Bang, the universe was a vast, dark expanse. Then something incredible happened. The very first stars ignited, bringing an end to the cosmic dark ages. This pivotal moment, known as the cosmic dawn, completely transformed everything. For the first time since the initial afterglow of creation faded, there were sources of light in the cosmos. But these weren't like the stars we see today. They were massive, incredibly brilliant, and destined to live fast and die young, setting the stage for the universe as we know it. These first stars, which we call population 3 stars, were a breed apart. They formed from the pure, pristine hydrogen and helium left over from the Big Bang, with virtually no heavier elements. Because of this unique composition, they could grow to truly enormous sizes. We're talking 100 to 300 times the mass of our own sun. Without the heavier elements, or metals as astronomers call them, that help modern gas clouds cool and break apart, these primordial clouds collapsed into single supermassive stars instead of clusters. These giants burned unbelievably hot and bright, with surface temperatures over 100,000 Kelvin. That's more than 15 times hotter than the sun. They shone with the light of millions of suns, but their extreme mass meant their lives were fleeting, lasting only a few million years before they met a spectacular end. So how did these giants come to be? It all started inside vast halos of dark matter that had been growing since the universe's early days. These halos acted as gravitational wells, pulling in the primordial gas. As the gas fell in, it was squeezed and heated up. Now normally gas cools down by radiating energy away, but that process is much more efficient when heavier elements are present. Since this early gas had none, it had to rely on a much less effective coolant, molecular hydrogen. This inefficient cooling meant the gas had to become incredibly compressed before it could collapse further, which naturally led to the formation of these exceptionally massive stars. When the core of one of these collapsing gas clouds hit a staggering 10 million Kelvin and became dense enough, the magic began. Nuclear fusion ignited. Protons, the nuclei of hydrogen atoms, started fusing together to create helium, releasing an immense amount of energy in the process. This outward push of radiation pressure perfectly balanced the inward pull of gravity, stopping the collapse in its tracks. A star was born. Every single second, this fusion process converted 4 million tons of mass into pure energy, following Einstein's famous equation E=mc². This energy is what made the star shine. For the first time in hundreds of millions of years, the universe had beacons of light cutting through the primordial darkness. These population 3 stars didn't just shine in isolation, they dramatically altered their surroundings. Their intense ultraviolet radiation blasted through the neutral hydrogen gas for hundreds of light years in every direction, carving out massive, expanding bubbles of ionized plasma. This radiation was so powerful, it also destroyed the molecular hydrogen that other stars would need to form, effectively suppressing any new star birth nearby. On top of that, powerful stellar winds, blowing at thousands of kilometers per second, pushed even more gas away. In a way, the first stars were like cosmic vandals, clearing out huge cavities in the cosmos and transforming the pristine gas around them forever. After just a few million years of furious burning, these giants ran out of fuel and exploded as the universe's very first supernova. And these weren't just any supernovae. They were what we call pair instability supernovae, a uniquely violent event where the star's core becomes so hot that gamma rays turn into pairs of electrons and positrons. This suddenly removes the pressure supporting the core, leading to a catastrophic collapse and a titanic explosion that completely obliterates the star, leaving no black hole or neutron star behind. The energy released was more than 100 times that of a typical supernova, a blast visible across a huge portion of the early observable universe. This is where the story gets really exciting. Those first supernovae were the cosmic forges that created the universe's first heavy elements. Inside the explosive inferno, Rapid nuclear reactions cooked up everything from carbon and oxygen to iron and gold, all the elements heavier than hydrogen and helium. For the very first time, the cosmos contained the building blocks for complexity. These newly forged elements were blasted out into space at incredible speeds, mixing with the primordial gas clouds. The next generation of stars would be born from this enriched material, setting the stage for planets, complex chemistry, and eventually, us. The seeds of the second generation of stars, known as population 2 stars, were sown in the ashes of the first. Even a tiny amount of these new heavy elements, as little as 1 atom for every 1,000, radically changed how stars formed. Metals are excellent coolants, allowing gas clouds to radiate heat away much more efficiently. This meant the clouds could cool down faster and fragment into many smaller pieces. Instead of a single 200 solar mass monster, these enriched clouds formed clusters of smaller stars, ranging from less than our Sun's mass to maybe 50 times its size. These stars lived much longer lives, and some of them are still around today, ancient witnesses to cosmic history. Now you might be wondering, have we ever seen one of these first stars? The short answer is no, not directly. They lived too long ago and for too short a time, but we are actively searching for them. The James Webb Space Telescope is our ultimate time machine, peering deep into the universe's first billion years. It's hunting for the telltale signs of population 3 supernovae, or the first galaxies that hosted them. Even if we can't see a single one, their collective light might be detectable as a faint background glow. Astronomers are also searching our own galaxy for extremely metal-poor stars that could be survivors from that very early second generation. As more and more of these first stars formed, lived, and died, their bubbles of ionized hydrogen began to grow and overlap. Between 400 million and 1 billion years after the Big Bang, these bubbles merged to fill the entire universe. This process, called cosmic reionization, transformed the cosmos from a place filled with neutral, opaque gas into one filled with transparent, ionized plasma. For the first time, light from the earliest galaxies could travel freely across vast cosmic distances. This marked the true end of the Dark Ages and the beginning of the structured, illuminated universe we recognize today. With each new generation of stars, the universe became progressively richer in heavy elements. Population 2 stars created even more metals, which they scattered in their own death throes. Population truck stars, the modern generation, which includes our Sun, formed from gas that contained about 2% metals. This ongoing chemical evolution was absolutely essential for complexity to arise. Metals allowed dust grains to form, which are the seeds of planets. They enabled smaller, longer-lived stars to form. And of course, they provided the raw materials for rocky planets and the very chemistry of life itself. The earliest star clusters that are still around today, the beautiful globular clusters, are made of population 2 stars that formed less than 1 billion years after the Big Bang. These dense, spherical swarms of hundreds of thousands to millions of stars are ancient time capsules. All their stars were born at the same time from the same gas cloud. By studying them, astronomers can look at stars that are nearly as old as the universe itself, giving us clues about the timeline of this grand cosmic story of creation and enrichment. So, when you look up at the night sky, remember this incredible legacy. Every star you see, including our own Sun, is a descendant of those first magnificent population 3 giants. The oxygen you're breathing right now, the carbon in your body, the iron in your blood, every single heavy atom was forged in the heart of an ancient star that lived and died long before our solar system even existed. Stars didn't just pop up randomly in the vastness of space. They were born in bustling neighborhoods, in groups and clusters, all drawn together by the inescapable pull of gravity. Eventually, these clusters grew into something truly colossal: galaxies. These are massive, gravitationally bound cities of stars, holding anywhere from millions to trillions of suns. The story of galaxy formation started in the universe's very first billion years, and it's a story that's still being written today, through cosmic collisions and the continuous birth of new stars. This epic process is what transformed the smooth, almost uniform baby universe into the breathtaking, complex cosmic tapestry we see all around us. But what gave galaxies their shape? The secret lies in something we can't even see: dark matter. Think of dark matter as the invisible scaffolding of the cosmos. It makes up a whopping 85% of all matter, and under gravity, it clumped together into a massive cosmic web, a network of long filaments connecting dense hubs with vast empty voids in between. This structure grew from the bottom up. Small halos of dark matter merged to form bigger ones over billions of years. Regular matter, the stuff we're made of, was just along for the ride. It followed the gravitational pathways laid out by the dark matter, flowing along the filaments and pooling into those dense halos. The biggest of these dark matter concentrations, holding the mass of trillions of suns, became the birthplaces of the most massive galaxies. And this cosmic web isn't just a thing of the past, we can still see its pattern today. Galaxies aren't scattered randomly across the sky. They trace the ancient filamentary structures established by dark matter in the early universe. The very first galaxies, often called proto-galaxies, would look completely alien to us. They weren't the graceful spirals or glowing orbs we know today. Instead, they were small, messy, chaotic collections of stars and gas. We're talking about systems with maybe 100 million to 1 billion times the mass of our Sun, tiny compared to our Milky Way, which weighs in at 1 trillion solar masses. But what they lacked in size, they made up for in energy. These early galaxies were star-making factories, churning out new stars at a rate hundreds of times faster than our galaxy does now. These little dwarf galaxies were the fundamental building blocks. Over billions of years, they merged and merged again, a process called hierarchical assembly. Small galaxies combined to form larger ones, which then merged to create even bigger systems, eventually sculpting the massive galaxies we see in the modern universe. This idea of hierarchical assembly is key. It's a bottom-up process, where the smallest things form first and then combine to make bigger and bigger structures. Imagine 2 dwarf galaxies on a collision course. Over hundreds of millions of years, they would merge into one. Their stars would mix together, and their invisible dark matter halos would combine. This new, larger galaxy would then continue its journey, eventually merging with others and growing steadily over time. Our own Milky Way is a product of this cosmic construction project, built from countless mergers over 13 billion years. We can even see the evidence. All around our galaxy there are faint streams of stars, the ghostly leftovers of smaller galaxies that the Milky Way devoured millions or even billions of years ago. And this process isn't over. The Milky Way is currently in the process of absorbing several smaller dwarf galaxies, and we're on a collision course with our giant neighbor Andromeda, with the big crash set for about 4 billion years from now. Here's a real head-scratcher. Supermassive black holes existed when the universe was incredibly young. Astronomers have spotted quasars, objects powered by monstrous black holes, with the mass of hundreds of millions or even billions of suns, shining brightly when the universe was less than 700 million years old. How did they get so huge, so fast? It's one of the biggest mysteries in cosmology. One leading theory suggests they formed from the direct collapse of massive clouds of gas, creating seed black holes of 10 to 100,000 solar masses that then grew incredibly quickly by constantly gobbling up surrounding material. Another idea is that remnants of the very first stars merged together in the dense centers of early galaxies and grew from there. Whatever their origin, these giant black holes didn't just sit there. They had a profound impact on the galaxies they called home. These supermassive black holes at the hearts of galaxies acted like cosmic thermostats, regulating how their host galaxies grew and evolved. This process is called active galactic nucleus feedback, or AGN feedback. When a black hole was actively feeding on gas and dust, it would unleash a tremendous amount of energy in the form of radiation and powerful jets of particles. This energy would heat up the surrounding gas to millions of degrees. This superheated gas couldn't cool down enough to clump together and form new stars, effectively shutting down or quenching star formation in the most massive galaxies. In fact, our computer simulations predict that without this feedback, giant galaxies would be packed with far more stars than we actually observe. The fact that a galaxy's properties are so tightly linked to the mass of its central black hole strongly suggests that they grew up together, influencing each other's evolution every step of the way throughout cosmic history. There was a time when the universe was a true stellar nursery, bursting with activity. This cosmic noon happened when the universe was about 2 to 3 billion years old. During this peak period, galaxies across the cosmos were forming stars at a rate 10 times faster than they are today. Galaxies were rich in gas, the raw fuel for starbirth, and they underwent intense bursts of creation, making millions of suns worth of new stars every single year. Frequent mergers and collisions between galaxies were common, which acted like a funnel, channeling gas into the galactic centers. This not only triggered massive waves of star formation, but also fed the growing supermassive black holes. But since that frantic peak, the universe has been quieting down. The rate of star formation has steadily declined as galaxies have used up or blown away most of their easily accessible gas. Plus, with the universe constantly expanding, it's just getting harder for fresh gas to gather together and kickstart the whole process again. So how did we get elegant spiral galaxies like our own Milky Way? It all comes down to spin. As those early protogalaxies merged, the gas within them began to swirl. Thanks to the conservation of angular momentum, the same principle that makes a spinning ice skater speed up when they pull their arms in, the gas spun faster and faster as it fell toward the center. This motion flattened the cloud of gas into a thin, rotating disk. New stars were born within this disk, creating the flat plane of stars we see in spiral galaxies today. The beautiful spiral arms aren't solid structures, but rather density waves. Think of them like cosmic traffic jams. Stars and gas bunch up temporarily as they orbit through these waves. This compression can trigger a new round of star formation, which is why the arms shine so brightly with hot, young blue stars. This entire process of disk formation took billions of years, and it's still being fed today by a slow trickle of gas from smaller, minor mergers. And what about the other main type of galaxy? The giant ellipticals. These galaxies have a completely different origin story. They are the result of major mergers, violent head-on collisions between two galaxies of roughly the same size. When two large spiral galaxies collide, the organized spinning motion of their stars is thrown into chaos. Instead of orbiting neatly in a disk, the stars are tossed onto random, crisscrossing paths, creating a big spheroidal or football-shaped distribution. These dramatic mergers often trigger one last intense burst of star formation that quickly uses up all the available gas. The result is what astronomers call a red and dead galaxy, a reddish-colored elliptical filled with old stars and very little new star birth. These behemoths tend to be the largest and most massive galaxies in the universe, and they are most commonly found at the heart of huge galaxy clusters, where cosmic collisions were a frequent occurrence. Seeing these different shapes, the famous astronomer Edwin Hubble decided to classify galaxies by their appearance, or morphology. This system, known as the Hubble sequence, groups them into spirals, ellipticals, and a catch-all category for the oddballs, called irregulars. What started as just a visual catalogue, we now understand as a map of different evolutionary paths. Spirals, with their beautiful disks, likely formed relatively peacefully through the gradual collection of gas, avoiding any major collisions. Ellipticals are the product of those violent, disk-destroying major mergers. And irregulars often represent young galaxies that are still in the chaotic process of being assembled, or dwarf galaxies that haven't quite settled down. This rich diversity in galaxy shapes reflects the complex dance between mergers, star formation, gas accretion, and black hole feedback that has sculpted our universe over billions of years. So, how do we know all this? We can look back in time. Thanks to amazing tools like the Hubble Space Telescope, we can peer deep into the cosmos and see galaxies as they were billions of years ago. Pictures like the Hubble Ultra Deep Field show us thousands of galaxies at all different stages of their evolution. Because light takes time to travel, looking at distant galaxies is literally looking into the past. And now, the James Webb Space Telescope is pushing that boundary even further, allowing us to see some of the very first galaxies that formed in the universe's first 500 million years. And what do they look like? They're small, clumpy, irregular, and glowing blue with intense star formation. Exactly what our theories of hierarchical assembly predict. By studying their sizes, shapes, and how fast they're making stars, we can test our models of galaxy formation against the real thing. Zooming all the way out, the large-scale distribution of galaxies today, the cosmic web, traces its origins all the way back to tiny, random quantum fluctuations that happened fractions of a second after the Big Bang. Over 13.8 billion years, gravity amplified those tiny seeds, stretching them into the vast, filamentary structure we observe. Massive clusters of galaxies sit at the busy intersections where these filaments meet. Smaller groups and individual galaxies are strung along the filaments like pearls on a string, and in between, there are enormous cosmic voids, vast expanses of near emptiness. This incredible structure is a treasure map, holding clues about the nature of dark matter, the mystery of dark energy, and the very initial conditions of our universe. And what about our place in all of this? Our Milky Way is part of the Local Group, a modest collection of galaxies that includes two other large spirals, Andromeda and Triangulum, along with dozens of smaller dwarf galaxies. We're situated on the outskirts of the massive Virgo supercluster, which itself is just one piece of an even grander structure called the Laniakea supercluster, home to over 100,000 large galaxies. Our cosmic address is a direct result of billions of years of this bottom-up hierarchical formation, placing us in a relatively quiet neighborhood within the vast and beautiful cosmic web. Have you ever wondered what the universe looked like right after it was born? Imagine getting a baby picture of the entire cosmos. Well, we have one. It's called the Cosmic Microwave Background, or CMB. This is the oldest light in the universe, photons that have journeyed for 13.8 billion years to reach us, from a time when the universe was a mere toddler, just 380,000 years old. It's a snapshot of the cosmos before a single star or galaxy had formed. This faint microwave glow, completely invisible to our eyes, surrounds us from every direction, a silent testament to the Big Bang. The story of its discovery is a classic tale of scientific serendipity. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were using a massive horn antenna at Bell Labs. They were trying to do some radio astronomy, but were plagued by a persistent, annoying hiss, a background noise that came from everywhere in the sky. They checked everything. They even cleaned out pigeon droppings from the antenna, thinking that might be the source. But the noise wouldn't go away. Frustrated, they consulted with physicists at nearby Princeton University, who had a stunning realization. This wasn't noise. It was the afterglow of creation itself. Penzias and Wilson had accidentally found the cosmic microwave background, the remnant radiation predicted by the Big Bang theory. This single discovery provided overwhelming evidence for our cosmic origin story and rightly earned them the Nobel Prize in Physics in 1978. So where exactly does this ancient light come from? It originates from what scientists call the surface of last scattering. Picture a sphere all around you, but a sphere in time as well as space. This marks the moment when the universe cooled down enough for protons and electrons to combine and form the first atoms. Before this recombination, the universe was a hot, dense, opaque soup of charged particles. Light couldn't travel freely. It just bounced around like a pinball. But once atoms formed, the universe suddenly became transparent. The photons were set free, and the light we see today as the CMB is from those photons, finally escaping and beginning their epic journey across the cosmos. That surface is now 46 billion light-years away due to the expansion of space. And here's a mind-bending thought. Every observer in the universe is at the center of their own surface of last scattering. You are literally at the center of your observable universe. The most striking feature of the CMB is just how incredibly uniform it is. No matter which direction you look, its temperature is almost exactly the same. 2.725 Kelvin, just a couple of degrees above absolute zero. The temperature is consistent to 1 part in 100,000. To put that in perspective, if the CMB were a sphere the size of the Earth, the biggest variations would be smaller than a speed bump. This near-perfect smoothness was actually a huge puzzle. How could regions of the sky that were too far apart to have ever been in contact have the exact same temperature? The leading explanation is a period of hyper-fast expansion in the first fraction of a second after the Big Bang, known as cosmic inflation. It took a tiny, uniform patch of the universe and blew it up to cosmic proportions, ensuring everything started at the same temperature. But it's the tiny imperfections that tell the most interesting story. When scientists analyze the pattern of these hot and cold spots, they find something amazing. Sound waves. Yes, sound waves in the early universe. In the primordial plasma, gravity was trying to pull matter together, while the intense pressure of radiation was pushing it apart. This cosmic tug-of-war created massive pressure waves or acoustic oscillations that rippled through the early universe. When the universe became transparent, these oscillations were frozen in place, imprinted onto the CMB. By studying the size and strength of these frozen waves, what's called the power spectrum, cosmologists can measure the fundamental properties of our universe. The most prominent peak tells us the universe is geometrically flat. The other peaks reveal the precise recipe of the cosmos, how much ordinary matter, dark matter, and dark energy it contains. But temperature is only half the story. The light from the CMB is also polarized, meaning its light waves tend to vibrate in a preferred direction. This polarization gives us another layer of information. There are two types of polarization patterns, E modes and B modes. E modes, which were first detected in 2002, are caused by the same density fluctuations that create the temperature spots and confirm our standard model. B modes are the holy grail. They are much fainter and can be created by the gravitational pull of massive structures distorting the light, but also tantalizingly by primordial gravitational waves, ripples in space-time itself, generated during cosmic inflation. Detecting these primordial B modes would be direct smoking gun evidence for inflation and would open a window into the universe's very first moments. Our understanding of the CMB has been shaped by a trio of legendary space telescopes. First came COBE in 1989. It made the groundbreaking first detection of the CMB's anisotropies, proving they existed and earning its lead scientists a Nobel Prize. Then came WMAP, which operated from 2001 to 2010. It created a much more detailed map, pinning down the age, composition, and geometry of the universe with incredible precision. Finally, the Planck satellite, from 2009 to 2013, gave us the ultimate high-resolution view, measuring temperature differences down to millionths of a degree. Each mission built upon the last, painting an increasingly clear picture of our cosmos and confirming the standard cosmological model with breathtaking accuracy. So, what have we learned from this single source of ancient light? The CMB has given us the universe's vital statistics. We know the universe is 13.8 billion years old, give or take just 20 million years. We know it's geometrically flat. We know its ingredients. About 5% is the ordinary matter that makes up stars, planets, and us. 27% is mysterious dark matter, and a whopping 68% is the even more mysterious dark energy driving cosmic expansion. We've even measured the current expansion rate, the Hubble constant. The CMB is a cosmological treasure trove, revealing so much about our universe from a single all-sky picture. The CMB isn't just a static baby picture. It also acts as a backlight, illuminating everything between us and the early universe. As CMB photons travel towards us, they sometimes pass through massive galaxy clusters filled with hot gas. The energetic electrons in this gas can give the photons a tiny energy boost, a phenomenon called the Sunyaev-Zeldovich effect. This creates tiny distortions, shadows, and bright spots in the CMB map where the clusters are. By looking for these distortions, astronomers can find and catalog galaxy clusters across the sky, even those that are too distant to see otherwise, helping us test models of how large-scale structures form over time. There's another way the journey distorts the CMB light: gravitational lensing. According to Einstein's theory of general relativity, the gravity of massive objects like dark matter and galaxies can bend the path of light. As the CMB photons travel for billions of years, their paths are slightly deflected by all the structure they pass. This subtly twists and distorts the patterns of hot and cold spots we see. By carefully mapping these lensing distortions, scientists can reconstruct a map of all the matter, both visible and dark, throughout the universe's history. It's like using the CMB to see the invisible scaffolding of the cosmos, and the quest is far from over. A new generation of experiments is pushing the boundaries even further. Powerful ground-based telescopes in the Chilean Andes and at the South Pole are staring at patches of the sky with incredible sensitivity, hunting for the faint signature of primordial B-mode polarization. Future space missions are being planned to map the polarization of the entire sky with even greater precision. These experiments could finally give us direct proof of cosmic inflation, measure the mass of the elusive neutrino, and perhaps uncover new physics that will once again revolutionize our understanding of the universe. From its accidental discovery to the stunningly precise maps of today, the cosmic microwave background is arguably the single most important observation in all of cosmology. It confirmed the Big Bang theory, gave us the precise recipe of our universe, and showed us the tiny seeds from which all cosmic structure grew. This faint ancient glow connects us directly to our origins, a 13.8 billion-year-old message from a time before anything we know existed. It's a profound and beautiful glimpse into the birth of everything. What you see when you look up at the night sky, all the stars, galaxies, and glittering gas clouds, that's only 5% of everything in the universe. The other 95% is completely invisible, and we only know it's there because we can feel its gravity. About 27% of this invisible stuff is dark matter, a mysterious substance that doesn't emit, absorb, or reflect any light. The other 68% is dark energy, an even stranger force that's making the universe expand faster and faster. We are living in a cosmos dominated by things we can't see and don't yet understand. Back in the 1970s, the astronomer Vera Rubin was studying how galaxies spin and stumbled upon a huge puzzle. You'd expect stars on the outer edges of a galaxy to move slower, just like planets farther from the sun orbit more slowly. But that's not what she found. Instead, stars on the outskirts were zooming along just as fast as stars near the center. This meant there had to be a huge amount of invisible mass, a massive halo of it, extending way beyond the visible galaxy. This was the first solid evidence that galaxies are surrounded by dark matter. Galaxy clusters, which are massive collections of thousands of galaxies, gave us even more proof. Astronomers looked at how fast the galaxies were moving within these clusters and calculated the total mass needed to hold them together. They also measured the temperature of the hot gas between the galaxies to get another mass estimate. Both methods showed the same thing. There's way more mass than what we can see in stars and gas. In fact, about 85% of the mass in these clusters is dark matter. Then a third method called gravitational lensing, where the cluster's gravity bends light from galaxies behind it, confirmed it all. The most dramatic proof came from the Bullet cluster. This is actually two galaxy clusters that smashed into each other. When they collided, the hot gas from each cluster, which we can see with X-ray telescopes, crashed together and slowed down. But gravitational lensing showed that most of the mass just passed right through without stopping. This was the dark matter, separated from the regular matter. It proved dark matter is a real substance, not just a weird trick of gravity, because we could see its gravitational pull in a different place than all the visible stuff. So, what isn't dark matter? We know it's not just regular matter that's dark, like unlit stars or dust clouds. The Big Bang theory tells us exactly how much ordinary matter was created, and it's only 5% of the universe. Not nearly enough. It's not a bunch of black holes or dim stars either. We've looked for them and haven't found enough. And it's not neutrinos, those tiny ghost-like particles, because they're too light and fast to clump together and form the structures we see. The Bullet cluster also rules out the idea that we just misunderstand gravity. Dark matter has to be a completely new type of particle, something beyond our current understanding of physics. The leading candidate for this new particle is something called a WIMP, which stands for Weakly Interacting Massive Particle. These are hypothetical particles that would be 10 to 1,000 times heavier than a proton and would barely interact with anything except through gravity. A theory called supersymmetry naturally predicts a particle just like this, the neutralino, which would be stable and have all the right properties. Plus, calculations show that the Big Bang would have created just the right amount of WIMPs to account for all the dark matter we see today. But even after decades of searching, we haven't found one yet. Another popular idea is the axion. These particles would be incredibly lightweight, millions of times lighter than an electron, and would interact so weakly they'd be almost impossible to find. Originally, they were proposed to solve a completely different problem in particle physics, but they turned out to be a great dark matter candidate too. Instead of individual particles, axions would form a kind of invisible field filling all of space. Scientists are building special experiments that use powerful magnetic fields to try and coax axions into turning into photons, which we could then detect. So, where is all this dark matter? It forms immense, invisible halos around galaxies. These halos are densest at the center and spread out far beyond the visible stars. The Milky Way's own dark matter halo probably extends out 600,000 light-years, which is 6 times farther than our most distant stars. On an even grander scale, dark matter forms the cosmic web, a vast network of filaments stretching across the universe. Galaxies and galaxy clusters form at the densest intersections of this web. The visible universe is just the glowing froth on a deep, dark ocean of matter. Dark matter wasn't just a bystander. It was the construction foreman for the universe. In the early cosmos, radiation pressure was so intense that regular matter couldn't clump together to form galaxies. But dark matter, being immune to radiation, started collapsing into gravitational wells much earlier. When the universe cooled down enough for regular matter to break free from the radiation, it fell straight into these pre-made dark matter molds. This gave galaxy formation a massive head start. Without dark matter, computer simulations show a universe with tiny, late-forming galaxies, nothing like the one we live in. Scientists are in a global race to find this stuff. They've built incredibly sensitive detectors deep underground, shielded from cosmic radiation, just waiting for a single dark matter particle to bump into an atom. The biggest experiments use tons of supercooled liquid xenon, watching for a tiny flash of light that would signal a collision. But so far, nothing. This lack of discovery has actually been useful, ruling out many of the simplest WIMP models and pushing physicists to think about new possibilities. Another way to hunt for dark matter is through indirect detection. The idea is that if 2 dark matter particles smash into each other, they could annihilate, producing a burst of detectable particles like gamma rays. So, telescopes scan regions we know are full of dark matter, like the center of our galaxy, looking for this excess gamma ray glow. There have been some tantalizing signals, but they could also be caused by normal astronomical objects like pulsars. We need a clearer, unmistakable signal to be sure. But the dark matter story still has some confusing chapters. Our simulations predict that dark matter should be very densely packed into the centers of galaxies, creating a cusp. But when we look, we often see flatter cores. The simulations also predict that big galaxies like ours should have hundreds of smaller satellite galaxies, but we've only found a few dozen. These puzzles might mean our simulations are too simple, or they could be a clue that dark matter has more complex properties than we thought. Dark matter remains one of the biggest mysteries in all of science. It makes up 85% of all matter, yet we have no idea what it is. Around the world, the hunt continues with more sensitive detectors, more powerful telescopes, and brilliant new ideas. Whether it's a WIMP, an axion, or something no one has even dreamed of yet, finding it will change everything we know about the universe. The search is driven by one certainty: it's out there. Back in 1998, astronomers made a discovery so shocking it would eventually win them the Nobel Prize. They found that the expansion of the universe isn't slowing down as it's speeding up. Think about that for a second. Galaxies aren't just moving apart, they're rushing away from each other faster and faster over time. This completely defies what we thought we knew. Gravity, the force that pulls everything together, should be acting like a cosmic brake, slowing things down. But something else is out there, a mysterious force that's flooring the accelerator, pushing the universe apart with ever-increasing strength. We've given this mystery a name: dark energy. And it's not some minor detail. It makes up a staggering 68% of everything that exists. So how did we figure this out? The key was observing a special kind of stellar explosion called a Type Ia supernova. These happen when a specific type of star, a white dwarf, goes kaboom. What's amazing about them is that they are standard candles, meaning they all have a predictable, known brightness. It's like knowing every 100-watt light bulb is equally bright. By measuring how dim one of these supernovae appears from Earth, we can calculate precisely how far away it is. We also measure its redshift, which tells us how fast it's moving away from us. In 1998, two separate teams of scientists were studying these distant explosions. They expected to find evidence of gravity slowing down the expansion, but they found the opposite. The distant supernovae were dimmer and therefore farther away than they should have been. This was the smoking gun. For the last 5 billion years, the universe's expansion has been accelerating. Ironically, the first person to predict something like dark energy was Albert Einstein, way back in 1917, though he later called it his biggest blunder. When he first applied his new theory of general relativity to the entire universe, the math showed it had to be either expanding or contracting. But the common belief at the time was that the universe was static and unchanging. So to make his equations fit that idea, Einstein added a fudge factor he called the cosmological constant, represented by the Greek letter lambda. It was a kind of anti-gravity force to keep the universe from collapsing. Then, in 1929, Edwin Hubble discovered the universe was expanding, and Einstein famously ditched the cosmological constant. But here's the twist. It looks like he was right the first time. That constant, representing an energy inherent to the very fabric of space itself, is currently our best explanation for dark energy. As the universe expands, more space is created, and with it, more of this energy, driving the acceleration. The leading candidate for this energy of space comes from the bizarre world of quantum physics. Quantum field theory tells us that even a perfect vacuum isn't empty. It's fizzing with virtual particles that pop in and out of existence, creating what's called vacuum energy. The problem? When physicists try to calculate how much energy this should create, the number they get is absurdly huge. It's 1 followed by 120 zeros times larger than what we actually observe. This is, without a doubt, the single worst prediction in the history of physics. Why the actual energy of the vacuum is so unbelievably tiny is one of the deepest, most baffling puzzles in all of science, known as the cosmological constant problem. To get a better handle on what dark energy is, scientists look at its equation of state, which is a ratio of its pressure to its density, represented by the letter W. For regular matter, W is 0. For light, it's 1/3. But for dark energy, all our measurements point to W being -1. This means dark energy has negative pressure. That's a mind-bending concept. Instead of pulling things together like gravity, it actively pushes space apart. This is exactly what Einstein's cosmological constant predicts. And so far, evidence from supernovae, the afterglow of the Big Bang, and the large-scale structure of the universe all agree. WABU is very, very close to -1. But not every scientist is convinced it's the cosmological constant. Some have proposed alternative ideas. One is called quintessence, which imagines dark energy as a dynamic field that changes over time, unlike a constant. This would mean its W value might not be exactly -1. Other theories suggest that maybe Einstein's theory of general relativity itself needs to be modified on cosmic scales. A more exotic idea is phantom energy, where W is less than -1, which would lead to a very dramatic end for the universe. For now, the simplest model, the good old cosmological constant, fits the data best. But we're still looking for any hint that it might be something more complex. This whole thing leads to another head-scratcher, the coincidence problem. Why now? For most of the universe's 13.8 billion year history, matter was the dominant force, and its gravity held sway. Dark energy was always there, but it was just a background whisper. As the universe expanded, the density of matter thinned out, while the density of dark energy stayed constant. It was only in the last few billion years that dark energy finally took over and started the acceleration. We just happen to be living in the exact cosmic era when the densities of matter and dark energy are roughly equal. Is this just a random coincidence? Or is there a deeper reason? Some argue that we have to live at this time because any earlier and there wouldn't have been time for stars, planets, and life to form. But this explanation doesn't sit well with many physicists. The evidence for dark energy isn't just from one source. It's overwhelming and comes from multiple independent lines of inquiry. Type Ia supernovae show us that distant galaxies are farther than they should be. The cosmic microwave background, the faint heat left over from the Big Bang, tells us the universe is geometrically flat, which requires the extra energy density of dark energy to make the numbers add up. Baryon acoustic oscillations, which are ancient sound waves frozen into the distribution of galaxies, act as a cosmic ruler, and they also confirm the accelerated expansion. Even counting galaxy clusters and studying how light is bent by gravity on cosmic scales all point to the same inescapable conclusion. About 68% of our universe is made of this mysterious dark energy. So, what does this mean for the future? If dark energy is indeed a constant, the universe is headed for a cold, lonely end. The acceleration will continue, pushing galaxies farther and farther apart. Eventually, every galaxy outside our own local group will be moving away so fast that its light will never reach us again. They will vanish beyond our cosmic horizon, leaving our sky empty. Star formation will eventually stop. The stars will burn out. All that will be left are black holes and stellar remnants, which themselves will eventually evaporate over trillions upon trillions of years. The universe will end in a heat death, a state of maximum entropy near absolute zero, forever dark and empty. But what if dark energy isn't constant? What if it gets stronger over time? This leads to a more violent scenario known as the Big Rip. In this case, the ever-strengthening expansion would eventually become so powerful it would overcome all other forces. First, it would tear apart clusters of galaxies. Then, the galaxies themselves would be ripped asunder. Solar systems would be unbound, and eventually the expansion would be so extreme it would tear apart planets, stars, and even individual atoms. Fortunately, our current data suggests W is -1, which avoids this fate, but we can't completely rule out phantom energy just yet. To figure this all out, we're launching some of the most ambitious observational projects in history. The Dark Energy Survey has already mapped hundreds of millions of galaxies. The upcoming Vera C. Rubin Observatory will track billions of galaxies and thousands of supernovae. Space telescopes like Euclid and the Nancy Grace Roman Space Telescope will map the cosmic web in unprecedented detail. These missions are designed to measure the properties of dark energy with incredible precision, hoping to finally determine if it's a constant or if it changes over time. Ultimately, understanding dark energy is about more than just cosmology. It touches the very foundations of physics. The cosmological constant problem signals a massive gap in our understanding of either gravity or quantum mechanics. Some ideas in string theory suggest a multiverse with trillions of possible universes, each with a different amount of vacuum energy, and we just happen to live in one that allows for our existence. Solving this mystery won't be easy. It will likely require a revolution in physics, as profound as relativity and quantum mechanics were a century ago. So there you have it, dark energy. It dominates our universe, it dictates its ultimate fate, and it completely defies our best theories. We've measured it, but we have almost no idea what it is. It remains perhaps the deepest and most compelling mystery in all of science, and solving it could unlock a new understanding of reality itself. Is our universe the only one? Or is it just one bubble in a vast cosmic ocean, a multiverse of countless other universes, each with its own laws of physics, maybe even its own dimensions? This idea, once purely science fiction, now springs from some of our most advanced theories in physics, like inflation, string theory, and quantum mechanics. It's a controversial and mind-bending concept, one that pushes the boundaries of what we can know. But it also represents one of the boldest and most profound ideas in all of cosmology. One of the main roads to the multiverse comes from the theory of cosmic inflation. This is the idea that our universe underwent a period of explosive, exponential growth in the first tiny fraction of a second after the Big Bang. Now, what if that inflation never completely stopped? In a model called eternal inflation, it continues forever in the vast expanse of space. But here and there, like bubbles forming in a boiling pot of water, inflation does stop in small pockets. Each of these pockets becomes its own universe, with its own Big Bang and its own unique physical laws. Our entire observable universe would be just one of these bubbles in an eternally inflating sea, with an infinite number of other universes constantly popping into existence, forever beyond our reach, separated by an ever-expanding space. Another path to the multiverse comes from string theory. This is our leading candidate for a theory of everything, aiming to unite the two pillars of modern physics, quantum mechanics and gravity. To make the math work, string theory needs more than the 3 spatial dimensions we experience. It requires 6 or 7 extra dimensions, all curled up on a scale so tiny we can never see them. The mind-boggling part is that there are a colossal number of ways these extra dimensions can be curled up, something like 10 to the power of 500. Each unique way creates a different set of physical laws, different particle masses, different strengths for the fundamental forces, a completely different reality. So, if eternal inflation creates the bubbles, string theory provides the blueprint for what each bubble can become, resulting in a vast landscape of universes where every mathematical possibility is made real somewhere. This brings us to one of the biggest puzzles in physics, the fine-tuning problem. Our universe seems exquisitely balanced for life. If the strength of gravity or the mass of an electron were just slightly different, stars wouldn't form, complex chemistry wouldn't be possible, and we simply wouldn't be here. Why is our universe so life-friendly? The multiverse offers a solution called the anthropic principle. If there are countless universes, each with different physical laws, it's no surprise that we find ourselves in one of the rare ones that allows for conscious observers. It is like asking why we find ourselves on a planet with liquid water, because life as we know it needs it to evolve. Most universes would be sterile and empty. This explanation, however, makes many physicists uneasy, because it feels like giving up on finding a deeper, more fundamental reason for why the laws of nature are what they are. Then there's the multiverse proposed by quantum mechanics. The many worlds interpretation suggests that every time a quantum event happens with multiple possible outcomes, the universe itself splits into different branches. In one branch, Schrödinger's cat is alive. In another, it's dead. Each branch is a complete, parallel universe. Unlike the bubbles of eternal inflation, these universes all share the same fundamental laws of physics, but differ in their history of quantum events. Think of it as an infinitely branching tree of realities. This is a mathematically clean way to deal with the weirdness of quantum mechanics, but it comes with the heavy philosophical price of accepting an unimaginable number of parallel worlds that we can never, ever interact with. Pushing this idea to its absolute limit, physicist Max Tegmark proposed the mathematical universe hypothesis. He suggests that every mathematically consistent structure, every possible set of equations, describes a real, physical universe. Our universe, with its specific laws, is just one of these mathematical objects made real. This ultimate multiverse would contain universes with different numbers of dimensions, different fundamental particles, and laws of physics that would be completely alien to us. In this view, physics is simply the study of which mathematical structure we happen to inhabit. While a fascinating philosophical idea, it's a step too far for most scientists, as it moves from the realm of testable science into pure speculation. But could we ever find actual evidence for a multiverse? It's a long shot, but maybe. If another bubble universe bumped into ours early in cosmic history, it might have left a bruise in the cosmic microwave background, the leftover radiation from the Big Bang. We could look for a specific circular pattern in the temperature of this radiation. In fact, astronomers have found some strange anomalies like the CMB cold spot, a curiously large cool patch in the sky. While this could be a sign of a cosmic collision, it's more likely just a random statistical fluke. For now, there's no smoking gun evidence, and many physicists are skeptical that we'll ever be able to directly prove other universes exist. It's no surprise that the multiverse is one of the most hotly debated topics in physics today. Supporters argue that it's a natural consequence of our best theories, like inflation and string theory, and that it provides the most logical explanation for the fine-tuning of our universe. On the other side, critics argue that a theory that can't be tested isn't science, it's philosophy. If we can never observe these other universes, how can we ever prove they're real? They worry that the multiverse is a dead end, a way of giving up on the search for deeper answers. The debate really gets to the heart of what science is and how it should be done. If the multiverse is real, the philosophical implications are staggering. It would be the final step in the Copernican revolution. Not only is our planet not the center of the universe, but our entire universe isn't special either. It's just one of an infinite number. In a multiverse where anything that can happen does happen, what does that mean for ideas of cosmic purpose or design? It also creates weird paradoxes for probability. How can you make predictions when everything happens an infinite number of times? These are questions that blur the line between physics and philosophy, forcing us to rethink what we mean by reality and our place within it. Of course, the multiverse isn't the only explanation for fine-tuning. Some physicists hold out hope for a final theory of everything that will show the values of the physical constants are not random, but are mathematically required to be exactly what they are. There's no other option. Others suggest that life might be more adaptable than we think, capable of arising in universes with very different laws. And some even propose that consciousness itself plays a fundamental role in shaping the laws of physics. Each of these alternatives avoids the need for a multiverse, but comes with its own set of immense challenges. A similar, equally mind-bending idea is the simulation hypothesis. This proposes that our entire universe could be a highly advanced computer simulation created by a more advanced civilization. Think of the Matrix, but on a cosmic scale. If it's possible for a civilization to create such simulations, and they create many of them, then simple statistics suggest it's more likely we are in one of the many simulations than in the one base reality. This idea is essentially impossible to prove or disprove, but it does make you wonder, are the laws of physics fundamental truths, or are they just the programmed rules of the simulation we're living in? Whether the multiverse is real or not, thinking about it has already had a huge impact on cosmology. It has forced scientists to grapple with fundamental questions about what makes a theory scientific and how we can test ideas that seem to lie beyond our observational reach. This debate has helped clarify which parts of our theories are on solid ground and which are more speculative. In a way, by pushing the boundaries of science, the multiverse concept helps strengthen the scientific method itself. So, is our universe a unique, singular existence, or is it just one page in an infinite cosmic library? This might be a question we never answer for certain. The multiverse remains a tantalizing idea, born from our best physics but perhaps forever beyond our grasp. Whether it is a profound glimpse of the ultimate reality or just a beautiful piece of mathematical fiction, the idea of the multiverse is a powerful reminder of how much we still have to learn. How will the universe end? For centuries, this question was reserved for theology and philosophy, but today physics and cosmology can give us concrete answers based on real observation and theory. The ultimate fate of our universe hinges on a few key things: what it's made of, its overall shape, and the mysterious nature of dark energy. There are several possibilities on the table, from an endless, quiet expansion to a catastrophic, fiery collapse, each leading to a profoundly different end of everything. So which one is it? For a long time, we thought it all came down to a cosmic balancing act. The key was something called critical density, the exact amount of stuff needed to make the universe perfectly flat. If the universe had more stuff than this critical amount, it would be closed and gravity would eventually win, pulling everything back together in a big crunch. If it had less, the universe would be open and expand forever. And if it was just right, a flat universe expanding forever but slowing down over time. And guess what? Our best measurements of the cosmic microwave background, the afterglow of the Big Bang, tell us our universe is astonishingly flat. But here's the twist. A mysterious force called dark energy is causing the universe to accelerate its expansion. This acceleration overpowers gravity, meaning even in a flat universe, the expansion is speeding up. It seems the universe is destined to expand forever, no matter what. So if it's expanding forever, what does that actually look like? The most likely scenario, if dark energy stays constant, is called the heat death. But don't let the name fool you. This isn't an end by fire, but by eternal cold and darkness. As the universe expands faster and faster, it will push distant galaxies so far away that we'll never see them again. In about 1 trillion years, the gas needed to form new stars will run out. The last stars will eventually burn out, leaving behind a graveyard of white dwarfs, neutron stars, and black holes. Over unimaginable stretches of time, even these cosmic remnants will slowly decay. The mightiest black holes will evaporate through a process called Hawking radiation, a process that could take a Google, that's a 1 followed by 100 zeros, years. In the end, all that will be left are lonely, scattered particles adrift in a cold, dark, and ever-expanding void. A universe effectively dead and approaching absolute zero. The timeline for this heat death is just staggering, operating on scales that are hard to even wrap your head around. Let's try. In 100 trillion years, the very last star will flicker into existence. A quintillion years from now, even the longest-lived stars will have died out. Fast forward to 10 to the power of 30 years, and all the dead stars will have either been swallowed by black holes or flung out of their galaxies. By 10 to the 65 years, if protons are unstable, as some theories suggest, matter itself might start to fall apart. And finally, after 10 to the 100 years, the last supermassive black holes will have evaporated into nothing. What's left? An eternity far longer than all the time that came before it, where single particles drift through an empty, expanding space, never encountering anything. A universe where nothing ever happens, and time itself loses all meaning. But what if dark energy isn't constant? What if it gets stronger over time? This hypothetical substance called phantom energy would lead to a much more violent end, the Big Rip. In this scenario, the accelerating expansion would become so powerful it would overcome every other force in nature. It would be a rapid, cascading destruction. First, clusters of galaxies would be torn apart. Then the galaxies themselves would be ripped to shreds. Soon after, solar systems would come undone as gravity loses its grip. Planets, moons, and asteroids would crumble into dust. The force would become so strong it would break apart molecules, then pull electrons away from atoms. In the final moments, atomic nuclei would shatter, and maybe even the quarks inside protons would be torn apart. This entire cosmic disintegration, from galaxies to subatomic particles, would happen in a finite time, maybe just 20 billion years from now. While our current observations suggest this is unlikely, we can't completely rule it out just yet. Now let's flip the script. What if dark energy weakens, or even reverses, becoming attractive instead of repulsive? Then we might face the big crunch. The expansion of the universe would slow, stop, and then reverse. Galaxies would start rushing toward each other. The night sky, instead of growing darker, would grow brighter and bluer as the light from approaching galaxies gets compressed. As space itself contracted, everything would get hotter and denser. Galaxies would collide and merge into a single chaotic firestorm. The universe would race back towards the state it began in, an infinitely hot, infinitely dense point, like the Big Bang in reverse. Based on what we see today, with dark energy showing no signs of slowing down, the Big Crunch seems highly improbable. But our understanding of this strange energy is still in its infancy. But maybe a Big Crunch isn't an end, but a new beginning. Some fascinating theories propose a big bounce. In this model, as the universe collapses, quantum gravity effects would kick in and prevent it from crushing into a singularity. Instead of a crunch, it would bounce back, triggering a new Big Bang and creating a brand new universe. This could mean we live in a cyclic universe, one that has gone through endless cycles of expansion and contraction. Each new universe could even have slightly different laws of physics. It's a mind-bending idea that suggests our Big Bang might not have been the first, and our universe might one day give birth to another. While this is still highly speculative, it's an active area of research in cosmology, ready for a really unsettling possibility. It's called vacuum decay. Quantum physics suggests that the vacuum of our universe, the empty space itself, might not be truly stable. It could be in a false vacuum state, like a ball resting on a ledge instead of in the deepest part of the valley. A random quantum fluctuation could, at any moment, anywhere in the cosmos, create a bubble of the true lower energy vacuum. This bubble would expand at the speed of light, and inside it, the laws of physics would be completely different. Constants of nature would change, making atoms, molecules, and life as we know it impossible. Because this wall of cosmic change moves at the speed of light, we would have absolutely no warning before it hit us and rewrote reality. While current calculations suggest our vacuum is probably stable for a very, very long time, we can't be 100% certain. In an eternal universe heading for heat death, we run into a strange paradox, the problem of Boltzmann brains. Over infinite time, random quantum fluctuations could theoretically assemble particles into a conscious mind, complete with a single fleeting thought or memory. These spontaneously formed Boltzmann brains would be far, far more common than beings like us, who evolved over billions of years in a complex, orderly universe. So, statistically, we should be one of these fleeting, disembodied brains. The fact that we are not, that we experience a consistent reality with a past and future, suggests that something might be wrong with our current model of an eternal, fluctuating cosmos. It's a deep puzzle that cosmologists are still trying to solve. So all these far future fates, can we actually test them? The answer is yes, by looking at the universe right now. The precise nature of dark energy is the key. By making incredibly detailed maps of the universe, we can measure how the expansion has changed over cosmic history. Missions like the Vera Rubin Observatory, the Euclid Space Telescope, and the Roman Space Telescope will observe billions of galaxies to create the most precise measurements of cosmic expansion ever. These observations will tell us if dark energy is a constant or if it's getting stronger or weaker over time. This data will help us narrow down the possibilities and give us a clearer picture of how our universe will ultimately end. With all these cosmic doomsday scenarios, you have to wonder, could any form of intelligent life survive? In a heat death scenario, perhaps, advanced civilizations might huddle around the last dying stars or figure out how to extract energy from spinning black holes. Some even speculate that consciousness could be encoded in a way that survives the cold, empty future. But a big rip? That seems utterly unsurvivable, as the very fabric of physics is torn apart. In a big bounce, it might be possible to pass information through the crunch into the next universe. It's a fascinating thought experiment, blurring the line between science and philosophy, asking if complexity and consciousness can find a way to cheat cosmic death. Ultimately, we have to be humble. All these predictions are based on our current understanding of physics, and we know our understanding is incomplete. There could be new forces or new physics that only appear over vast timescales or at extreme energies. We still don't have a working theory of quantum gravity, which is essential for understanding singularities like the Big Bang or a potential Big Crunch. Dark energy itself remains a profound mystery. While heat death appears to be the frontrunner based on today's evidence, the universe could still have some major surprises in store for us. Whether our universe ends in a cold whimper, a violent rip, or a fiery crunch, these destinies are so far in the future they are almost beyond comprehension. Right now, we are living in the universe's golden age, an era where stars shine brightly, galaxies dance across the cosmos, and the universe is complex enough to give rise to life. Our existence is just a brief, precious moment in the grand cosmic story. It's a moment between a simple beginning and an ultimate quiet end, a moment where the universe can wake up and, for a short time, wonder at itself. Even with all our amazing progress, we're still staring at some of the biggest mysteries in the universe. What really kicked off the Big Bang? What exactly are dark matter and dark energy? Was there an inflation period, and what caused it? Is our universe the only one out there? These questions aren't just academic, they're the new frontier of cosmology, where what we can see meets the very edge of what our theories can explain. Each new discovery here could completely rewrite our understanding of everything. So let's start with the ultimate question. What came before the Big Bang? Now, this question might not even make sense. If time itself started with the Big Bang, then there was no before, just like there's nothing north of the North Pole. But that doesn't stop physicists from speculating. Maybe our universe popped into existence from a random quantum flicker in a vast multiverse. Or maybe it's the latest bounce from a previous universe that collapsed in on itself. Some even suggest it was born inside a black hole in a higher dimensional reality. Theories like loop quantum cosmology and string theory offer some mathematical paths to explore these ideas, but we have zero observational evidence. The honest truth is, we might never know what, if anything, came before our cosmic beginning. Now here's a real head-scratcher called the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, it's almost the exact same temperature everywhere. But here's the catch. Parts of the sky on opposite sides were so far apart back then, they should have never been able to exchange heat and even out their temperatures. They were never in causal contact. So how did they end up so uniform? The leading theory is inflation. It suggests that in the first tiny fraction of a second, the universe expanded exponentially, stretching a tiny connected region to become the entire observable universe we see today. But we haven't found the smoking gun for inflation yet. Detecting specific patterns called B-mode polarization from gravitational waves created during inflation would be a home run, but so far no luck. Other ideas, like bouncing universes, might also explain this uniformity, so the debate is still very much alive. And what about dark matter? It makes up a whopping 85% of all the matter in the universe, but we still have no idea what it is. For decades, we hunted for particles called WIMPs, but the search has come up empty. This has forced scientists to get more creative. Maybe dark matter is made of axions, super light particles that we're trying to detect by seeing if they turn into photons inside powerful magnets. Or it could be sterile neutrinos, a heavier cousin to the neutrinos we already know. Another possibility is primordial black holes formed in the chaos of the early universe, or it could be something totally out of left field, interacting through a force we haven't even discovered yet. Each of these ideas requires a completely different kind of experiment. Until we actually detect one of these particles, the true nature of dark matter will remain one of science's biggest puzzles. If you think dark matter is a mystery, dark energy is on a whole other level. This strange force is causing the expansion of the universe to accelerate, and it makes up 68% of everything. But what is it? Is it the cosmological constant, a fundamental energy woven into the fabric of space itself? Or is it a dynamic field that changes over time, sometimes called quintessence? The biggest problem is the sheer value of it. When physicists try to calculate how much dark energy there should be based on quantum theory, their answer is off by 120 orders of magnitude. That's a 1 followed by 120 zeros. This isn't just a small error. It suggests we're missing something huge about gravity or quantum mechanics. Some have even proposed that our theory of gravity, Einstein's general relativity, might be wrong on cosmic scales. For now, a simple cosmological constant fits the data best, but our understanding is frankly embarrassing for something that dominates the entire universe. Here's another fine-tuning puzzle, the flatness problem. As far as we can measure, the universe is geometrically flat, but according to standard Big Bang theory, this shouldn't be the case. Any tiny bit of curvature in the early universe, whether positive or negative, would have been magnified exponentially over 13.8 billion years. For the universe to be as flat as it is today, its initial state had to be flat to an accuracy of 1 part in 10 to the power of 60. That's like balancing a pencil on its tip for billions of years. It seems impossibly fine-tuned. Inflation theory solves this neatly by stretching space so much that it naturally becomes flat, like how the surface of a giant balloon looks flat to an ant on it. But without confirmation of inflation, the flatness problem remains a major cosmic coincidence we can't quite explain. And why are we even here? The Big Bang should have produced matter and antimatter in perfectly equal amounts. Whenever a particle of matter meets its antimatter twin, they annihilate each other in a flash of light. So logically, the universe should be filled with nothing but leftover energy. And yet here we are, made of matter. The only way this is possible is if there was a tiny imbalance at the start. For every billion pairs of matter and antimatter particles, there was just one extra particle of matter. After all the annihilation, this tiny leftover became all the stars, galaxies, and planets. We know the basic conditions needed for this to happen, but the known laws of physics just don't create a big enough imbalance. This means there must be new physics out there beyond our current standard model to explain our very existence. What that physics is, nobody knows. Then there's the lithium problem. Big Bang nucleosynthesis is a cornerstone theory that brilliantly predicts how much of the light elements, like hydrogen and helium, were created in the first few minutes of the universe. The predictions match observations perfectly, except for lithium. The theory says we should see 3 to 4 times more primordial lithium-7 than we actually find in the oldest stars. This gap has puzzled scientists for decades. Did some unknown nuclear reaction destroy the lithium? Did the stars themselves somehow burn it off their surfaces? Or does it point to some new physics that was active during the universe's infancy? The lithium problem is a small but persistent crack in our otherwise incredibly successful model of the Big Bang, hinting that we're still missing a piece of the puzzle. One of the most heated debates in cosmology today is the Hubble tension. The Hubble constant is the rate at which our universe is expanding right now. Simple enough, right? The problem is, when we measure it in different ways, we get different answers. When we look at the local universe using things like supernovae and special pulsating stars, we get a value of about 73 kilometers per second per megaparsec. But when we look at the early universe using the cosmic microwave background, the data points to a slower rate, about 67. The difference is now so precise that it's statistically significant. It's not just a random error. This tension could mean our measurements are wrong, or it could be pointing to brand new physics. Maybe dark energy isn't constant, or maybe there were unknown particles in the early universe. This puzzle is a big deal because solving it could lead to our next major breakthrough in understanding the cosmos. And if you look closely at the cosmic microwave background, things get even weirder. There are several anomalies or features that don't quite fit the standard model. For instance, the temperature variations on the very largest scales are weaker than predicted. There's a giant cold spot that is much larger and colder than should be statistically likely. The two hemispheres of the sky seem to have slightly different average temperatures. While these could just be statistical flukes, after all, we only have one universe to look at, they might also be clues to something deeper. Some theories suggest they could be signs that the universe is finite in a weird way. Or maybe they are echoes from a time before inflation, or even bruises left over from a collision with another universe. For now, these cosmic anomalies remain tantalizingly unexplained. So we've talked about mysterious particles, but what if dark matter isn't a new particle at all? What if it's made of primordial black holes? These aren't the black holes left by dying stars. They would have formed from super-dense pockets of matter in the first second after the Big Bang. This idea is attractive because it doesn't require any new particle physics. It's just regular matter squeezed into an extreme state. However, we've looked for them. Searches for their gravitational effects, known as microlensing, and other observations have ruled them out as the only source of dark matter in most mass ranges. But there are still a few windows open. Primordial black holes with masses similar to asteroids, or those around 10 to 100 times the mass of the Sun, could still be out there. The hunt is on, as finding them could solve a huge cosmic mystery with physics we already know. Finally, why does time only move forward? The fundamental laws of physics, from gravity to electromagnetism, are time-symmetric. They work just as well in reverse. A video of planets orbiting a star would look perfectly normal if you played it backward. Yet we all experience time as a one-way street, an arrow of time. The common answer is entropy or disorder, which always increases in a closed system. But that just pushes the question back. Why was the universe in such a low entropy, highly ordered state at the very beginning? This initial condition seems incredibly fine-tuned, Perhaps it's just the only kind of universe that could support life, or maybe our understanding of time and the Big Bang is still missing a fundamental ingredient. These questions, and so many others, are what drive cosmology forward. What is quantum gravity? Does the multiverse exist? How did supermassive black holes get so big, so fast? For every question we answer, it seems like a dozen new ones pop up. Our cosmic knowledge is vast, but what we don't know is even vaster. The universe still holds its deepest secrets close, challenging us to keep looking, to keep building better tools, and to continue this incredible human quest to understand where we came from. 13.8 billion years ago, the universe exploded into existence from a singularity of infinite density. In that very first second, fundamental forces separated, particles began to form, and matter won its narrow, crucial victory over antimatter. Within just a few minutes, the first atomic nuclei assembled. It took another 380,000 years for atoms to form, allowing light to finally travel freely across the cosmos. Hundreds of millions of years later, the first stars ignited, lighting up the cosmic darkness. Galaxies assembled, merged, and evolved over billions of years. And here we are now, a part of the universe that has become conscious, able to look back and understand its own incredible beginning. The Big Bang isn't just a wild guess. It's established science, backed by an overwhelming amount of evidence. We see every distant galaxy rushing away from us, a clear sign of cosmic expansion. We've photographed the cosmic microwave background, a faint afterglow from when the universe was just 380,000 years old. And it looks exactly as the theory predicted. The amounts of light elements like hydrogen and helium in the cosmos perfectly match the calculations of Big Bang nucleosynthesis. The vast, web-like structure of galaxies we see today grew from tiny quantum fluctuations in the universe's earliest moments, and the gravitational waves we detect from colliding black holes confirm the mind-bending predictions of general relativity. All these independent lines of evidence point to the same solid conclusion. The universe began in an incredibly hot, dense state and has been expanding and cooling ever since. Through cosmology, we've uncovered truths far stranger and more magnificent than any ancient myth could have imagined. We've learned that space and time are not eternal. They had a definite beginning. We know the universe is not only expanding but accelerating, and it might just expand forever. We've discovered that most of the universe is completely invisible to us. Dark matter and dark energy make up a staggering 95% of everything that exists. We now understand that the tiny, random fluctuations of the quantum world were the seeds that grew into the enormous galaxies we see today. The very elements that make up our bodies were forged in the fiery hearts of long-dead stars. We can now take pictures of black holes and listen to the ripples in space-time caused by cosmic collisions. We've managed to trace our cosmic history from the first microsecond all the way to the present day, measuring the universe's age, its contents, and its ultimate fate with a precision that would have seemed like pure fantasy just a few decades ago. This incredible understanding didn't come from just thinking about it. It required the development of truly remarkable technology. Giant ground-based telescopes peer across billions of light years, observing countless galaxies. Space satellites like Planck have mapped the afterglow of the Big Bang in stunning detail. Incredibly sensitive gravitational wave detectors like LIGO can measure distortions in space-time smaller than the nucleus of an atom. Powerful particle accelerators on Earth recreate the conditions of the Big Bang for a fleeting moment. And supercomputers run massive simulations, helping us visualize how the universe evolved over billions of years. Each technological leap has opened a new window on the cosmos. The Hubble Space Telescope gave us our first deep look into the distant universe. The James Webb Space Telescope is now showing us the very first galaxies as they formed. Technology is what transforms cosmology from a philosophical debate into a precise empirical science. For millennia, humans have looked up at the night sky and wondered about our cosmic origins, but we were limited to myths and speculation. Ancient civilizations became brilliant astronomers, mapping the stars and tracking the planets. Then thinkers like Copernicus and Galileo bravely revealed that Earth was not the center of the universe. In the 20th century, Edwin Hubble discovered that the universe was expanding. Einstein's theories predicted the strange and wonderful consequences of relativity. Then, almost by accident, Penzias and Wilson found the faint heat left over from the Big Bang. Vera Rubin's work uncovered the first compelling evidence for dark matter, and today, modern cosmologists measure the universe with unprecedented precision. This incredible journey, from a state of complete ignorance to our current deep understanding, represents humanity at its very best, curious, persistent, and willing to challenge our most cherished assumptions to follow the evidence wherever it leads. You know, you are more intimately connected to the cosmos than you might think. The hydrogen in the water in your body was formed in the first 3 minutes after the Big Bang. The carbon, nitrogen, and oxygen that make up your cells were forged inside stars that lived and died long before our sun even existed. The iron flowing in your blood came from the explosive death of massive stars called supernovae. The calcium in your bones, the phosphorus in your DNA, every heavy element that makes you you was created in a stellar furnace billions of years ago and scattered across the galaxy. You are literally made of stardust. Your atoms have journeyed for billions of years through space before coming together to form the complex, conscious being that is you. When the great Carl Sagan said, "We are a way for the cosmos to know itself," he wasn't being poetic. He meant it literally. Let's put our existence into perspective. The universe is 13.8 billion years old and stretches at least 93 billion light years across. It contains an estimated 2 trillion galaxies, and each of those galaxies has hundreds of billions of stars. Our Earth is just a tiny planet, orbiting an ordinary star, in the quiet suburbs of a typical spiral galaxy, located in a completely unremarkable region of this vast, vast universe. As a species, we've been around for about 300,000 years. That's barely 0.002% of all of cosmic history. And yet, in this cosmic eye blink on this pale blue dot, we've developed consciousness, built civilizations, and figured out the grand story of where we came from. We are simultaneously insignificant specks of matter and yet utterly extraordinary, because we are the specks of matter that can contemplate the universe's magnificent vastness. Despite all our incredible progress, profound mysteries still remain. What is the invisible dark matter that holds galaxies together? What is the mysterious dark energy that's causing the universe to expand faster and faster? Did a period of rapid inflation really happen at the dawn of time? Does a multiverse of other universes exist beyond our own? And the biggest questions of all, what came before the Big Bang? What is the true nature of quantum gravity? Why is there something rather than nothing? These are the questions that drive scientists today. Future telescopes will peer even further back in time to see the universe's infancy. Next-generation detectors will reveal more cosmic secrets through gravitational waves, and new particle experiments might finally uncover the identity of dark matter. Science is a journey that never ends. Every answer we find just generates new, deeper questions, driving us on an endless quest for understanding. The next few decades promise to be a golden age of revolutionary discoveries. The James Webb Space Telescope is already observing the universe as it was in its first 500 million years. Soon, the LISA mission will detect gravitational waves from the mergers of supermassive black holes at the centers of galaxies. The Vera Rubin Observatory will create an unprecedented map of billions of galaxies, tracking changes over time. The Roman Space Telescope will probe the nature of dark energy, and the future Einstein Telescope will observe gravitational waves with a sensitivity we can barely imagine today. These incredible instruments will undoubtedly answer some of our biggest questions, while just as surely raising brand new ones we haven't even thought of yet. The golden age of cosmology is far from over. It's continuing, with each generation building on the incredible discoveries of the past. So why does any of this matter? Why should we care about things that happened billions of years ago and billions of light years away? Because understanding our cosmic origins is profoundly important. It tells us where we came from, what we're made of, and where the universe is heading. It reveals our fundamental connection to the cosmos. We aren't just observers looking in, we are a part of it. It demonstrates the incredible power of human reason and curiosity to understand the natural world. It provides a powerful perspective on our own lives and our place in existence. This knowledge humbles us with the sheer vastness of the universe, while at the same time elevating us with the astonishing realization that we, on our tiny world, are capable of comprehending it. Cosmology isn't just about distant stars and galaxies, it's about understanding ourselves and our deepest origins. The story of cosmology is a stunning testament to the power of the scientific method. Through careful observation, brilliant mathematics, and clever experimentation, we have pieced together the history of the universe from its very first instant to the present day. We have rigorously tested our theories against the harsh light of reality, discarding ideas that failed and refining the ones that succeeded. We have built a global consensus based on evidence, not on authority or tradition. Scientists from different cultures, speaking different languages, and coming from different backgrounds all contribute to one single shared understanding of cosmic truth. Science works. It works because it is self-correcting, because it is based on evidence, and because it is open and transparent. The success of cosmology is a magnificent validation of the scientific method as humanity's most powerful tool for understanding reality. When you think about it, we are all extraordinarily fortunate just to exist. The universe could have collapsed back on itself in its very first second. The battle between matter and antimatter could have ended in a perfect tie, leaving behind nothing but light. The initial quantum fluctuations could have been different, preventing galaxies from ever forming. Stars might not have ignited. Our sun might not have had planets. Earth might not have developed life. Countless improbable steps, a long chain of cosmic accidents, had to happen in just the right way to lead to this very moment, to you, a conscious being, capable of contemplating the origin of the universe itself. This beautiful accident of cosmic evolution is something that truly deserves our wonder, our appreciation, and our gratitude. From the fiery flash of the Big Bang to the quiet, accelerating expansion of today, the universe has been on an epic journey for 13.8 billion years. From simple hydrogen gas to complex life, from a smooth, uniform plasma to a rich tapestry of stars and galaxies, the cosmos has evolved in ways that are both beautifully comprehensible and deeply mysterious. Our great quest to understand this evolution continues. Every new observation, every new theory, every new discovery brings us one step closer to comprehending our cosmic origins. The universe began in mystery, and it retains its mysteries still. But through science, through patience, and through our unending sense of wonder, we continue to unravel the greatest story ever told, the story of how the universe and everything in it, including us, came to be.